Hi guys, this is your lesson on linear quadratic systems of equations. You are going to need your packet and open it to page 41. We'll do some examples on that page. And then you're also going to need the half sheet that you got in class that has the flashcard information on it. And when the video is over, you're going to work on completing the questions on the flashcard sheet. All right, so what is a linear quadratic system? So linear indicates that we're going to have a line which has the equation y equals mx plus b. Quadratic indicates that we're going to have a parabola which has a standard equation of y equals ax squared plus bx plus c. Now, either of these equations may not be in that given form, but those are the forms they should be in when you go to graph them. And these are either going to be graphed together or solved together. And just like with regular systems of equations, we're looking for the common solutions, or if you're graphing, the points of intersection. So how many solutions can there be? First of all, the most common situation is that you can have two solutions to a linear quadratic system, and that's when the parabola and the line cross twice. Now, the line can go a lot of different directions in order for them to cross twice. Just here's one example for you with 2 points of intersection. Okay, a little less common, it is possible to have one point of intersection where the line just kind of grazes one point on the side of the parabola. That is called tangent to the parabola. The line is called tangent to the parabola. So it's only touching it once. And tangent is just the fancy word we use to describe that it's only touching the curve once. Lastly, we can have a linear quadratic system with no solutions. Here's one example of that. Another very common example would be a horizontal line that for a parabola with a minimum would be completely below the line. For example, on this one right here that we're looking at, on this example here, the x-axis itself, if we had that as an equation, that would in fact have no solutions as well. Okay, so those are the only situations we can come upon. Two solutions, which is the most common, one solution or no solutions. Okay, so we're going to take a look on page 41. Here's the two examples at the top of page 41, but we're going to change this a little bit. We're going to cross off the equations given for number 3, and we're going to use the equations from number 1 on number 3. So we're going to go ahead and use that as our example so that we can see these side by side. We're going to do an algebraic solution and a graphic solution, and then we'll be able to check and make sure the solutions are the same. We're going to start with the graphing solution. I wrote the new, or copied the new equations onto here, and you can copy them onto your paper or just draw that arrow over like I did. Okay, let's start with the line. The line is in y equals mx plus b form. This has a slope of 1, or 1 over 1, and a y-intercept of -3. So we're going to go ahead and plot a point at -3, as you can see on the screen here. That's always our beginning point. We begin at b. And then we're going to use the slope of rise 1, run 1 to plot more points. Okay, now as you do that, I want you to notice that I plotted every single point that fits on that graph. And the reason for that is because I do not know where the point of intersection or points of intersection are going to be. So I need to have my line drawn as accurately as possible. Okay, while you're finishing up graphing that too, I just want to point out that you always can use your calculator and like the table on your calculator to help you graph a line. But I always like to use y equals mx plus b just because it's quicker and I don't need a calculator. Okay, so moving on to the parabola, we are going to need our calculator here. Now I know a lot of you don't have one at home, so I'm going to show you screenshots of this. So here's what the parabola looks like. I analyzed the graph to get the vertex of 0.5 comma -6.25, and so this was a very important one to get the vertex for because that's not going to be on the table. So we're going to need that point. And then if you hit Control T, here's just a little snapshot of what that table looks like. You're going to need these points that are on the table. Okay, now you're going to need more because again, you're going to want to plot every single point that's possible to fit on the graph. So when you're using a calculator, you're going to want to scroll throughout the table to find more points. So here's what that's going to end up looking like, okay? So we have a point at -3, 6, -2, 0, -1, -4, 0, -6. The vertex that we got was at 0.5, -6.25. There's a point at 1, -6, a point at 2, -4, a point at 3, 0, and a point at 4, 6. So if you need to, pause the video so that you can get those points plotted and draw the parabola. Hopefully you'll draw the parabola a little bit better than I did. I kind of messed up in this section right here. But as I was plotting these points for my parabola, I noticed that one of the points over here and one of the points over here ended up being one of the points on the line. So I know that those are my points of intersection. Okay, so when I finish solving, it looks like this. I circle the points of intersection, and just like with when you had two lines with a linear parabola, you're also going to put solutions, and then we're just going to state as many as there are. So in this case, there's a solution at -1, -4, and at 3, 0. Okay, all right, moving on. We're going to solve this algebraically. So we're going to start by substituting. We're going, because the linear equation says y equals x minus 3, we're going to substitute x minus 3 to the other equation. You can see I drew an arrow to where it's going to go. So now we have x minus 3 equals x squared minus x minus 6. Okay, so in this second equation, I replaced the y and I kept the rest of it the same. Okay, so now I have a quadratic equation that is going to need to be solved by getting it equal to 0. So I'm going to get it equal to 0 by subtracting x and adding 3 on both sides. Now, why would I do it that way? We do not want to have a negative x squared. It makes it very difficult to solve. Okay, so if I want my x squared to stay positive, I need to move everything to that side. So that gives me 0 equals x squared minus 2x minus 3. Which I'm just going to rewrite as x squared minus 2x minus 3 equals 0, because that's the standard form of a quadratic equation. Now, you can solve this quadratic equation using any of the methods that you learned previously. The square root method, which actually doesn't work for this one, the factoring method, the complete the square method, or the quadratic formula. I'm going to tell you, though, right now, almost exclusively linear quadratic systems are factorable. So that's the best way to go. It will be the quickest way to do this. So we're going to factor this with AM. We're going to find two numbers that add to -2 and multiply to -3. Okay, and those two numbers are -3 and 1. So I have x minus 3 times x plus 1. Because this is equal to 0, I'm going to do my t-chart. The t-chart gives me answers of +3 and -1. And then after that, you can see I plugged those into the original linear equation. So I would always suggest you go back to the linear equation. You can go to the quadratic, but the linear is better. So y equals x minus 3. Down here, since x was 3, I have 3 minus 3, which is 0. And over here, I have to do it again. So if x is -1, then y is -1 minus 3, which is -4. So if you have two x's, then you're going to have to find y 2 different times using an original equation. That gives me solutions of 3, 0, and -1, -4. And if you take a look side by side, we have the same two solutions for the system algebraically and graphically. Okay, moving on to the next one, we're going to do the same thing. Okay, so we're going to use example 2 for both. And for our graph, we need to get y by itself. We're going to subtract 2x on both sides. So y equals -2x plus 2. Okay, and that gives us a slope of -2 and a y-intercept of 2. Okay, and I'm going to go quickly through this, but you can pause the video if you need to. We have a y-intercept of 2 and a slope of -2. And so this is what the line ends up looking like when you plot those points. Okay, plot a point at 2 and then down 2 over 1. To graph the parabola, again, we're going to use the calculator. So here's what that looks like. So I analyzed my graph to get a vertex of 1, 1. And then here's just a snippet of the table. There is actually one more point I think you can plot other than those. And that looks like this. Okay, so at -2, 10, there's a point, -1, 5, 0, 2, 1, 1, 2, 2, 3, 5, and 4, 10. Again, feel free to pause the video if you need to do that. Notice here we have a little bit of a tangent line, or we do have a tangent line. It's only hitting the parabola once. It's very difficult to see that because of the kind of thickness of the pens or markers that you're using, but it does only hit that one time. And so we have a solution at 0, 2, and that's the only spot for that solution. Okay, solving algebraically. This time we're going to substitute the quadratic into the linear because y is alone here. There is not a variable alone in the linear equation. So in the quadratic, we're going to take what y is equal to, which is this here, and plug it in over here. So that looks like this. So 2x plus x minus 1 quantity squared plus 1 equals 2. Now, this right here, this binomial squared, has to be multiplied out using FOIL, the moon method, the crab claw method, or the box method, whatever you like to call it. I always like to kind of go off to the side of my paper and do that, but for the sake of time, I already did that for you. So that turns out to be this trinomial right here. So now we have 2x brought down. X squared minus 2x plus 1 is what you get from FOIL, and then plus 1 comes down and equals 2 comes down. And now again, we have to get this equation equal to 0. So I'm going to combine like terms on the left-hand side. The x terms cancel out, so I just have x squared plus 2 equals 2. Okay, now there's two ways to do this. You can go ahead and get it equal to 0 and then factor and solve, or you can use the square root method, which is what I decided to do. So I subtracted 2 on both sides. That gave me, oops, sorry about that. That gave me x squared equals 0. When I take the square root on both sides, x is equal to 0. And you can see this is why there's only one solution, because the square root of 0 is not plus or minus 0 like we normally would have a plus or minus, because 0 isn't positive or negative. So we only have that one x solution. We're going to substitute that to the original linear equation, and we get an answer of 2, which gives us a solution of 0, 2. Okay? Again, pause this if you need to. If you need to stop and kind of copy, feel free to rewind if you need to listen to it again. Side by side, here's what our solutions look like, okay? So we have 0, 2 for both. If you ever get a situation algebraically that you think is weird, always go and graph it on your calculator to check first, because you will see there's a possibility for no solutions, which actually result algebraically in some very weird things that you just can't solve, okay? So you always want to use your calculator to help back you up. All right. So here's what that half sheet looks like that you should have, and I want you to do this example on your own. I do realize that for the parabola you might need a calculator, but don't forget there's phone calculators. You can go online and Google it, or just come in and borrow one from me to get that one parabola graphed, okay? Let me know if you need any help. Otherwise, I'll see you next class.